I'm Youssef Hamadi from the Constraint Reasoning Group. I work on optimization, satisfiability, and I'm going to talk about a new project related to building design. It's a smart building project, and in that project, our objective is to help the architect to automatically optimize their design and their output. So we do that in the following way. We take a design, and we are going to consider the main aspect of the design, like the wall, the windows, the orientation, the air conditioning, the heating, and all these main features. And we are going to automatically adjust these features in a way which will improve the overall cost or the overall thermal efficiency of the building. Our approach is non-intrusive, which means that we don't want to go against the building designer. When we are going to optimize the wall, for example, we will only consider inner layer of materials. When we will play with the windows, we will not remove windows, but we'll just try to resize them in a minimal way. So this problem amounts into a large, complex multi-optimization problem. Okay? It's a complex multi-objective problem with several things that we have to take into account, like the cost of the building, the thermal efficiency of the building, and things which are important but which do not really translate in a cost, but which are more related to comfort, which is, for example, the amount of natural light that you have in the building. So why are we doing that? We do that because building construction amounts to 40% of the worldwide energy consumption. And if you take this number, it's far more than the whole combination of all the transportation combined. So we spend more carbon footprint on building and doing building. And if we look closely at this 40%, in fact, you realize that 80% of this 40% comes from the operation of the building. The fact that you are going to run the building over a long period of time and you are going to consume energy just to maintain the activity of the building. So here is the workflow of the smart building project. So we start here on the right with the architect, which is using a CAD tool, which gives us its original design. So we take a full description, a full CAD description of a real design, a real building in the system. With this design, we are going to run an optimization loop that you see here, which is going to adjust the design, create alternative design automatically by using an optimization formalism called genetic programming for people who are interested by that aspect. All this is possible because we are going to evaluate the design with a simulation engine. And this simulation engine is able to give us the energy, the thermal efficiency of a given building design. So this piece of code is very important. It has been done by the Department of Energy in the United States. It's 40 years of research. And it's a very well advanced and really state-of-the-art simulator which can evaluate a building and gives us calculation results like thermal efficiency, for example. So we take the original design, we create alternative design, we run the optimization loop, and each time we call this simulation engine. And eventually, at the end, we can go back to the designer with a set of alternative design, which are more energy efficient, which are eventually cheaper, which improve its original design automatically. The thing is that this workflow is very expensive to run because this simulation tool can be quite time-consuming. For one design, one evaluation of one design can take, for example, 40 minutes. Okay? And overall, to be efficient, we need to evaluate hundreds of solutions, hundreds of designs, hundreds of alternative buildings. So we do that. We run the whole workflow on Azure. And that's where the cloud comes in. This application, this smart building application, is really a typical simulation optimization application. And it shows the convergence between HPC, high-performance computing, and the cloud. So now we are going to move to the demo of the system, where I will show you the full workflow. I will start from a CAD tool here with a design. It's a building. It's a real building. I think it's a 500 square meter building with several rooms, etc., and internal courtyard. Well, you don't see all the detail here, but that comes from an architect. Okay. So I play the movie. So we can change the view. Of course, we are in full CAD mode here. And then at that stage, I'm starting the script where, if we slow down a bit, we see that we submit a job to the cloud with the given building, with a set of input which comes from the architect, which tell us which component of the design we are allowed to touch. For example, here we will see that we can touch all the wall, we can change the composition of the wall, and we can change the location of the windows and things like that. Okay, so we submit the job to the cloud. Okay, and then we see the HPC server portal where we can see that the job is running here. We can see the current state of the job, the number of resources which are used by this job, etc. So it amounts to a large number of small tasks. Okay, here we have a visual view of what's going on. In fact, you see here the actual state of the computation. So as I said, it's a multi-objective optimization problem. For this simulation with this building, we optimize the cost versus the energy consumption. Okay, each point here is a solution. Is a solution which has been automatically constructed and which has been automatically evaluated. Okay, and the designer, the building designer, can see that. But of course, this is an intermediate stage. We can move on. We can refresh the results, and we see the cost, the power consumption, and the cost here. And eventually, we can select one solution at the end of the calculation, and this is what we do here. Okay, this is what the end of the calculation. So on the left, we have the thermal evaluation of the original design, which was given by the architect, completely done by the architect. And on the right, you have what has been. You have the evaluation of a new design, which has been automatically defined by the tool. And if we look closely, we see that the new design consumes 53,000 kilowatts a year, while the original design consumes 55,000 kilowatts a year. So that means that in a few hours on Azure, automatically, for an architect, we can adjust its design and win, in that case, 4% on the thermal consumption of the design over a year. Okay? So in other scenario, we can go up to 10%. So it depends on the design, depends of course, on the quality of the original design and the amount of work put by the architect. So that's it. That's smart building.